In this session, I'm going to talk about exploratory factor analysis, which is another way of dimension reduction. Just like the principal component analysis that we have discussed earlier, the exploratory factor analysis also is one more approach that is used more widely across the various industries when we are trying to reduce the dimension of the data. So as a part of this session, we are going to look at what is this exploratory factor analysis, what are the various concepts that are a part of it, how does the exploratory factor analysis play a role in the data reduction, how do we really implement the EFA exploratory factor analysis in R, what do you mean by rotations, and how does the solution change when we are implementing rotations in exploratory factor analysis? How would you really visualize the solution of EFA? What are the interpretations you make by looking at the solution of EFA? What are the kind of plots that you can do on the exploratory factor analysis that comes out? Then one of the outputs of that exploratory factor analysis actually brings out factor scores. So how do I use those factor scores to interpret the factor variables? So these are the various aspects that we are going to look at in this session. So let's get started. The main purpose when I am looking at exploratory factor analysis, it is primarily trying to assess the relationship of the various constructs. Constructs, you can call them as various high level dimensions, right? Broad level aspects in surveys and psychological assessment. I do a survey, I have 20 questions, but I would like to see broadly 2 or 3 areas which how can I really understand the relationship across with respect to those 2 or 3 major areas in the survey or the assessment that I am performing. Those are the ones are typically called as factors. So those variables I cannot observe directly. For example, I am talking about customer satisfaction, right? This observation, I cannot observe what is customer satisfaction. But there are ways of trying to link something that can be observed with customer satisfaction. Basically, what is the kind of revisits the customer is making to a particular store? How many times he is doing a repurchase of a particular brand? So there could be some kind of mechanisms which can be observed, or there are some kind of metrics which can be measured or observed, which in a way we link them to satisfaction. So here when I am using the word factor, they are typically the latent variables. They cannot be observed directly, but I try to create some kind of an imperfect relationship with respect to other variables. See, number of revisits, it may not be directly a measure of satisfaction. Similarly, repurchasing a product may not be a direct correlation with the satisfaction, but all of them put together might define the satisfaction in a much better manner. So this is what we are trying to talk of here. So there is some latent variable which can't be measured or observed directly, but I can try to derive them through a set of many other variables which are called as manifest variables. Using them, some kind of relationship can be built, and finally some assessment regarding the satisfaction of the customer can very well be created. Now this part of it is what we are calling as exploratory factor analysis. I am exploring the factors based on the various variables that I am looking at. So in short, if I have to talk about what is the job of exploratory factor analysis, it will find the degree to which the composite factors which are latent, like satisfaction, they account for the observed variance of the manifested variable. So there is some kind of a variance that is present in the observed variables. Now what I want to look at is to what extent this observed variance is captured as a part of the latent factors which we are calling as the composite ones. So when I say satisfaction can be linked to revisit, repurchase, etc., I'm trying to see to what extent of the variation in the revisits and repurchases can be combined together to define something called satisfaction. So here the major thing is one variable that I'm looking at is a latent variable. So the customer satisfaction, the sensitivity of the prices, they are all latent variables. I cannot observe them directly, but I can link them to various other variables which can be observed, try to build some kind of relationships between them and try to have a good understanding of that. Now that is what we are typically calling as exploratory factor analysis. So the main job wise, it is trying to uncover the various latent dimensions that are present in the data. So it will see whether there are 2 dimensions, 3 dimensions. So there are some similarities with respect to principal component analysis also. But in the principal component analysis, the prime job that we have done is transform the data in such a way that they become the components that are typically getting created. They are all independent. They don't have any kind of correlation between them. So it's a pure matrices or mathematical kind of an operation. But here what we are saying is we are trying to link a latent variable to a set of variables which are the manifesting variables. So that's the small difference that you find between the PCA and the exploratory factor analysis. So even when you run it in R, the result looks more or less similar to PCA, where I'll get a matrix of factors, their relationship to the original variables. So we got like component 1, component 2, component 3, and all our variables V1, V2, V3. We get loadings, or we can also get the rotated component matrix. So more or less here also we get the same kind of result, a matrix of factors. These are the factors and their relationship with the original variable. So this is how we get the solution in the exploratory factor analysis as well. But the major difference is the solution, I look at it in terms of the manifesting variables itself. Maximally interpretable. To whatever extent I want to interpret my solution to a large extent in terms of the original variables itself, the latent variables are in turn manifested using the original variables, and whatever the solutions that I am looking at, they are talked in terms of the manifesting variables itself. So that is where I am saying the exploratory factor analysis is looking at the solution, small number of loadings for each factor. So I'll not look at all the loadings for each factor, every variable on every factor. I'm not looking at that. Here I'm looking at some kind of cutoffs where I typically see small number of loadings on each factor. So I will look at the magnitude, whether it is which loadings, which variables are highly loaded on each of the factors, and probably I may not even bother about those variables that are loaded very small on any of those factors. So which means the overall factors, instead of being looking at them as a composite linear combination of various variables, I'm looking at only a small set of variables influencing each of the factors. So that's the difference that you could see between the exploratory factor analysis and the principal component analysis. So again, it uses some concepts called rotations, right? We'll talk about different kinds of rotations, wherein initially it starts with a solution that a PCA might have created for you, where you have uncorrelated kind of data, uncorrelated kind of factors, because in a PCA also the output that we have seen, the correlation between the component that got created was zero. So when the correlations are zero, we are also calling it as orthogonal kind of solution. So means there is no intercorrelation that is existing between those variables. They are completely uncorrelated. So even the rotation that are performed in exploratory factor analysis, they take the output that comes out of the principal component analysis, where an uncorrelated solution is being taken, but to a large extent the loadings get, right here what happens is the loadings on the individual variables, they get adjusted. Different combinations of the loadings on the individual variables will be looked at, wherein the loadings on a couple of variables will be very high and the loadings on the others will be reduced, so that the component can be very clearly linked with a couple of variables only. So this is what we call as a rotation. So which means initially there will be a base solution which is an uncorrelated solution itself, but within that uncorrelated solution different combinations of the loadings will be tried out, right, keeping the overall variance still the same. Variance will not be compromised here, but what is typically looked at is instead of creating uniform load across all the variables, here we talk about more load being applied to one or two variables on each of the factors and the load on the other variables be removed, so that a simple linking of the variables to the latent factors can be done quite comfortably. So if you see here rotation, when something is being performed, I want to still maximize the loading on few variables. I'm not looking at uniform loading across all the variables, across all the factors. So there is some level of work that is happening where the loadings on a few factors by a few variables is trying to be maximized, but at the same time the correlation of zero is also getting maintained. So there are two objectives here. In a PCA, the major objective is make all the correlations zero, over. Whereas here, apart from making all the correlations zero, the focus is on loading more and more on a few variables. So let the weightages be much higher for a few variables for each of the component, so that not all variables are contributing in a similar manner to each of the component, and a component can be very well be attributed to the heavy contribution of one or two variables itself. So there are different kinds of rotations that are performed. So it's as good as the cutting is done differently. So the overall understanding and interpretation becomes much comfortable relative to the goal that we are going with. So the major part of the exploratory factor analysis that differentiates itself from the traditional principal component analysis is it is much doing different kinds of rotations, so that the loadings on the variables can be understood quite comfortably. The business interpretations can come out quite effectively compared to a PCA solution. So but let me put things in a right direction here. There is nothing which talks about any rotation is better or worse. But in some cases, when I try to bring in the business perspective to it, there is a very good possibility that some of them are very useful compared to the others. And much bigger difference between EFA versus PCA is in PCA, I am only looking in terms of the dimensions, but in exploratory factor analysis, I can still talk in terms of the original variables itself, because every factor has hardly two or three variables which are dominating in it. So when I'm talking about one particular factor, it means virtually I'm referring to these two or three variables itself. So I can very well interpret any kind of a result in terms of the original variables itself. But that would be very much difficult when we are doing it in principal component analysis. So EFA analysis is comparatively easier to interpret from a business decision making perspective compared to a principal component analysis. And at the same time, if I have conducted a survey, I can very well use it to refine a survey, because I can only keep those variables which have high loading on the factors, and I can very well remove those variables which do not have a high loading on the factors. So that way even my data collection efforts and everything else can be reduced, because I am looking at only those variables which are contributing heavily to factors, and I can remove those which do not have any kind of high correlations with any of the factors that are created. So this is very a useful item to investigate whether the surveys items that we have taken, they are all going together in line with the expectations or moving away from the expectations. So this is where the EFA becomes one of the powerful tools, especially when I am trying to identify the latent variables as a part of my survey kind of analysis. Now, how is EFA really contributing to the data reduction? First of all, let me tell you the factors. So few variables are combined together to form a factor. So any kind of analysis now, instead of analyzing each of these items separately, each of these variables separately, I can directly analyze this combined one. So I can use the factor score, which is a sum total or some kind of a combination of each of these various variables. So I can very well avoid the large set of variables, and I can use their proxy. This particular factor is a proxy for each of these variables. So wherever I want to analyze all these variables, I can use their proxy. So which means instead of dealing with a large set of variables, I am dealing with a very small set of variables. So if I am trying to assess the satisfaction, so instead of looking at all 10 questions that are dealing with satisfaction, I can typically look at one single component which is a reflection of the satisfaction, and I can take the analysis based on that one single factor which is a representative of all the 10 variables associated with the satisfaction. So that way there is a lot of dimension reduction that is happening. Even it can result in uncertainty reduction. So just think that satisfaction is linked with various variables, right? So instead of talking of each of these variables separately, if I take some linear combination of all these, because it's not a scientific relationship between the two. So because there is a lot of imperfection in terms of the relationships between the two, rather than taking each variable separately, if I take some linear combination of these variables, the noise can be reduced and the estimate will come much better. So the uncertainty or the noise is quite drastically reduced when I am going with the exploratory factor analysis. And at the same time, the data collection effort will come down. We have already discussed about it, because I will look at those variables which are contributing heavily to the first few factors, and those variables which are not at all contributing to the factors, I really need not bother about them. So my data collection efforts can be quite comfortably be reduced by going with exploratory factor analysis. So overall, these are the kind of advantages that the exploratory factor analysis can bring out, and which plays a very important role in the analytics aspect. So probably if I'm using some data, I really want to assess how many latent factors are there, right? Are there 2, 3, 4? How many latent factors are there? How do the various items that are there as a part of the survey, how do I map them to the latent factors? And based on the factors that are created, how can I link these factors across the various variables that are there in my data? Probably there could be something relating to the different brands that are there in my data. I want to really see how each of these factors change across the various brands. So how are these variables? How do they behave across all these factors? All these things I can very comfortably assess once I have created an exploratory factor analysis kind of a mechanism on my data. Now this is where let's go ahead in terms of taking a data, and based on that let's see how can we create an exploratory factor analysis solution. For doing this, I'm taking a simple data set in R, right, which is the branding related data. So this data brand ratings. So this is the data that I have pulled out from my folder. Let me look at the head of it. I called it as a brand. So the head of it is saying we are talking of different brands, ABCD. I think there are 10 brands in my data, right? And they are rated by the people in terms of performance, the leadership, whether they sell latest products or not. Is that brand a typical fun or serious bargain value, bargain for that particular products of that brand? What is the value the customer is enjoying? Is that brand a trendy kind of a brand, and would the customer be more and more interested in rebuying from that particular brand? So these are some of the things. And probably if I'm looking at the structure of the brand, yes, it's 1,000 observations, 10 variables. So all these are integers. The ratings that are given by the individual, they are integers. But brand is a factor with 10 levels A to J. So this is what is our data. So let me get into looking at a few small things. Determine the number of factors to estimate. So do I require 3 factors, 4 factors, 2 factors, 5 factors? How do I really assess how many factors to estimate? For that, I can use a scree plot, right? I can do a scree plot and retain the factors where the eigenvalue is greater than 1. I can do a scree plot. So once I do a PCA or once I do a factor analysis, so first let me do a PCA to start with, right? So I'll call it as brand PCA. I'll do PR comp, and I'm giving brand. I don't need all the columns. I'll remove the 10th column. So first thing is I should have actually done the scaling of the data as well. Now if I talk about the plotting of brand PCA, so this is what is the scree plot. By default it comes this way, but if I go with typing the type, where I set the type of it to line, where I set it to L, then I'll get it as a proper scree plot. So here I should be able to make out where there is a kink in the curve. So where it is becoming more and more flat, it is at that point I can say the number of components can be 2 or 3. So I can look at those factors where the eigenvalue is greater than 1, and just as an understanding here, the eigenvalue is nothing but it's a proportion. It's a metric for the proportion of the variance that is explained. Right? Take a correlation matrix and you can use the eigen function. right? But let's do that. So when I say eigenvalue, it's nothing but it's a proportion of the variance that is explained by that single factor. And why I am looking at 1? If the value is 1, I'm talking about that is the amount of variance that is contributed by one single variable. Now I want my factors to contribute to more variance than of one single variable, because I want them to be integrated across the variable. So the amount of variance that my factors have to really contribute to should be much higher than what my individual variable contributes. So I want to look at those particular values where the eigenvalue, those particular factors where the eigenvalue is greater than 1 itself, because I don't want really focusing on those factors which do not capture even a variance of one single variable to the fullest. So that is where eigenvalue of 1 means it is the amount of variance that is captured by one single independent variable. So I would always like to have the overall variance captured by my factor to be more than 1. So I'll set it to be equal to greater than 1. So now we can use the scree plot from this PR comp kind of a factory, from that PR comp operation, or the much better method, very interesting method, is use your n factors package. Right, let me use my n factors package, a very interesting package for factor analysis. Right, it has so many components, so many aspects that I can do with it. So let me see, I get a very interesting scree plot here. So that's one more reason I prefer the n factors package, where I use the n scree as the function within that. So let me first install the n factors package. All right. So let me load this package as well. Right, this package is being loaded as well. Now I can use the function called nscree. So which is a scree plot again, but with a slightly more information. So I can typically look at the overall data. Probably it would be better if I had taken the scaling. So let me do a scaling, or let me capture the scaled information separately. So let me call it as brand scale, where I take the scaled data. So I'll take scale on the brand. Instead of all the columns, I'll take -10. So I'll not include the 10th column in it. So only up to the first 9 columns I'll take. So this is where I can look at the head of brand scale, which will give me that, yeah, only the 9 columns are being considered. Now this is where I can do my nscree. On this data, let me do my nscree. So I'll do it on brand scale as the input. Error in the eigenform, correlation matrix must be symmetric. I think so. What is this brand scale? Let me take the summary of brand scale. Yes, it's a perform minimum maximum. So this is looking fine. Correlation covariance matrix must be symmetric. Okay, I need to take it on the correlation matrix. Let me just check. N scree. Alright. So I have to take N scree on the correlation matrix. N scree cannot be taken on the raw data. N scree I am taking it on the correlation matrix. Right. So let me tell it here. The N scree from the N factors, the input that I have to give to it is the correlation matrix of your data. Now what is happening is I could see that it has used 4 different kinds of methods, right? It has used NOC as a method, NAF. So these are different kinds of methods, right? So these kind of methods, they are being applied, and out of each of these things, it suggests how many factors are more appropriate going with each of these methods. At least I could see here there are 3 methods which are suggesting that there are 3 factors whose eigenvalues are more than 1. So 3 factors can be preferred, whereas there is one method that is saying only 2 factors are good enough. Whereas if I really want to look at the eigenvalues of each one of them, so this is one thing I can look at. First, N screen. I have plotted it on a correlation matrix. So in some methods, in most of the methods, I got that 3 factors are appropriate for this data. In some case, in one of the methods, I got that only 2 factors are appropriate. Now I can even look at the eigenvalues. Even the eigen is a part of the correlation matrix itself. So I'll use the function called eigen, and again on the correlation of the brand scale, I'll take this eigenvalues as well. So I'm getting my eigenvalues, yes, 0.237. So I'm getting my eigenvalues on each of these things, right? We have computed the correlation matrix. So these are what are the eigenvalues that are associated with each one. You could see 2.97, 2.09, eigenvalue is greater than 1, greater than 1. Here it is slightly greater than 1 for the third factor. But from the fourth factor onwards, the eigenvalues are much lesser than 1. So definitely from the fourth factor, I can very well ignore the stuff, ignore these factors, whereas the first two are looking more and more dominant. 3 is just above 1. That is where some of the procedures have given that 3 factors are significant, whereas some of them have given 2. So the first 2 of them are definitely greater than 1, whereas the third one is just marginally above 1. Now, out of this, which one do I need to use? So this part is purely specific to our business understanding, right? Probably I can check each of the solutions. Now here it is saying 2 in some cases, it's saying 3 in some cases. So I don't mind using both 2 and 3 and see to what extent this particular solution really fits to my business analysis. So once I have done the eigen analysis, I'm just looking at how many of them are above 1. So in some cases it's 2, in some cases it's 3. So which means I would like to check out these 2 different solutions that I'm getting by the scree as well as the eigenvalue results. Now when I have to perform this exploratory factor analysis, this is the function that I'm using. This is also from the base package itself, factanal, which is the function that we are using, right? I can very well specify how many factors I want, factors equal to 2, factors equal to 3. So I can very well say factanal brand scale, that is my data, right? So I'm taking a brand scale factor analysis, I'm taking, and I'm setting factors equal to 2. So this is what I can set, right? Probably to this, it's better that I add it's better that I add the headings so that I can really do the analysis at a later point in much better. So what I'll typically try doing is the brand scale, right? I will try to put row names. Let me take the row names of the brand scale. Let me set them as the variables from my scale brand. So brand, I'll take the 10th column values and I'll set them as the row names per brand scale. So if I right now look at the brand scale, it should have the row names which are similar to that. So A, and probably even if I'm looking at the tail of brand scale, it should be something to do with the J. So the names are coming out as the row names. So I'll maintain that. Now based on that, let's say I want to perform the factor analysis. So I'm calling a fact anal, where I'm looking at brand scale as the data and I'm setting my factors equal to 2. So I'm looking at the factor analysis being performed. So there are so many things that are coming out of this factor analysis. It talks about the uniqueness, right? So the performance is 63.5% unique, whereas latest is almost 80% unique, fun is 83% unique, trend is 70% unique, and rebuy is almost 60% unique. So there is one, so which talks about how much of interrelationship exists between these variables. Fun is looking like more and more unique, which means there is a very little interaction of fun with respect to other variables. The same way I can interpret about the latest and trendies, which do not carry too much of heavy relationship with the other. That is what is a measure of uniqueness. So the higher is the value, the lesser it is correlated with the other variables, and vice versa. Now you look at the loadings, right? Here we have given a two-factor solution. So here I could see factor 1, what are the highest variables? Some of them are typically eliminated here. You could see in PCA, when it was component 1, all the numbers were present. Factor 2, again in the component 2, all the variables were present. Here I could see at least 3 variables are knocked off in factor 1 and even 3 variables are knocked out in factor 2. And even if I look at here, the magnitude of the information plays an important role. On factor 1, I look at that bargain and value are very highly loaded. So these are the important things as a part of factor 1. So bargaining and having a value. So I can group these two variables together from the customer's perspective. They look at bargaining and the value being more or less similar kind of behaviors. Right, I can give a name to something that could be called with value plus bargain kind of variables. Similarly, if I look at factor 2, there is a heavy loading on leader. It's a market leader or something. And at the same time, I can talk about the seriousness that is associated with the product. So it's a serious product and it's a market leader. So something to talk of by combining these two kind of variables on factor 2. Whereas the other variables are not loaded on any of the things. If I look at fun, the impact is much lesser on both the factors. Latest, the impact is much lesser. It's not present in factor 2 at all, but in factor 1 also its importance is much lesser. Its contribution is much lesser. Right? The same goes with fun. Or even if I look at trendy, the same thing. It's not present in one of the variables, but it is very minute in the factor 1. So this is how it is coming as a two-factor solution. And similarly, you could see the total loading wise, factor 1 almost 24.9% of the variation, overall variance is taken care of by factor 1, and another 19% variation is taken care by factor 2. So overall I could see hardly around 44.5% of the total variation is taken care by factor 2. And here is the test of hypothesis also, that is saying two factors are sufficient. And the p-value being much less than 0.05, right, 8.66 into 10 to the power of minus 106, which is less than 0.05, which is a clear indication that the test, the null hypothesis has to be rejected. So the two factors are typically sufficient for the model. Now if I go with the three factor solution in this case, right, everything else remaining the same, I go with the three factor solution. If this also gives me, now if I see here the uniqueness wise, this is 62.4%, fun is 79.4, latest is almost nothing. So nothing is being captured regarding the latest as a part of the overall model. Fun still 79.4% is unique. It's not captured as a part of these three factors. Seriousness also, it's not fully captured. Whereas for the value, almost everything is captured. Only 20.2% is still unique. Latest, everything is captured. That is where only 0.5% of it is still unique. So whatever I am getting here, it's a measure that I have not captured it as a part of that particular variation, is not captured by any of my three factors that are produced. So there is still a lot of rebuy unique which is not captured into factor 1, factor 2, factor 3 and so on. Now even if I look at these three factors, the amount of variation they are capturing 20, 19 and 16, overall 57% is the total variation that they are able to capture. Now here also if you look at the definition of factor 1, it's very high on bargain and value, so still more or less the same. Factor 2 also is high on performance and the leadership, or probably seriousness. So these are the three things that are dominating in factor 2. And if I go to factor 3, looks like latest is the only kind of variable that is dominating in factor 3, trendy to some extent. So these are the things that are coming out as a part of each of the factors. And if I say a 9 factor solution, this is where you should be able to understand it better, right? Too many for 9 variables. So I really don't need to go for that much of a solution. So let me go with 4. When I go with 4, yes, my overall variation is only 3% contributed by the fourth factors. This is where the importance will typically go down. And I could clearly see in the fourth factor, none of the variables is dominating, right? The contribution of none of the variables is high. Whereas in three factors, the solution was much better. So I should always be focusing on a three factor solution for this problem, or at the max, if not three factors, then two factors, but definitely not four factors. That is what even my M-Scree has given when it has really tested out my correlation, said three factors are more and more sufficient enough. So the factor loadings which are near to 0, they are all omitted, right? Even if I go back to my three factor solution, this is my three factor solution. So these are all like zeros. So that's where they got directly omitted from my model. So that makes the PCA more and more compared to PCA, the exploratory factor analysis becomes more and more easier to interpret, because now I have only 5 variables in factor 1, and out of these 5 also, these 2 are looking more and more dominant, all others are looking very diluted. Same logic here, these 2 are looking more and more, or even this is looking slightly more dominant, all others are looking very diluted. So the interpretation becomes more and more comfortable when I am using the exploratory factor analysis compared to using the principal component analysis. So the factors that have almost zero correlation. So finally, when I look at the correlation between factor 1 and factor 2, right? Whatever the numbers that I get for factor 1 and factor 2, even that would that would be more or less completely uncorrelated itself, right? So which means that that portion is still continuing, that analysis is still continuing, but what is more and more important here is the interpretation becomes more simpler when I'm using an exploratory factor analysis solution. Then this is one more thing that we have to talk of in exploratory factor analysis, one more interesting topic, which is the rotations. We have to understand that whatever is the load, so rotations that happen, they are primarily, they play around with the loadings. So these are the loadings. So these loadings are typically played around with in such a way that the overall variation will still remain the same. These are the overall variances. Overall variances will still remain the same, but the loadings on very few variables will be much higher in each of the factors, and the loading of the other variables will be much lower. That is what are the rotations that are typically happening. So PCA, when we are talking of rotations, it's simply recomputing the transformations. When I say PCA, it is just recomputing the transformations of the observed data. Whereas in EFA, I'm trying to find the latent variables that may be observed with error. So that's a major difference. So the focus is on latent dimensions. What variables are contributing to a particular dimension is what is the objective of EFA, whereas PCA is purely mathematical, just transforming it into a different dimension such that the interrelationship between the variables is zero. The other way to understand the difference between a PCA and exploratory factor analysis is, here there is no necessity that my factors that I am getting, they are completely uncorrelated, right? It's not necessary for me to get a solution which is completely uncorrelated. I can still get correlated solution, right? But the difference is, I want the correlation to be more or less similar to what the real world scenario might be. So there are different kinds of rotations. In some rotations, I could find that the correlations will be zero, whereas in some rotations, the correlations may not be zero at all. And one such kind of a rotation that I want to bring in here is an oblique rotation. So wherein the rotation is nowhere an uncorrelated kind of stuff here. After the rotation, the solution that I get is not a uncorrelated kind of a solution. We will definitely find the correlation between the variables here. Right? So that is what we could not find in principal component analysis. But here the objective of the rotation is change the loadings on the variables in such a way that overall variance is still the same. Overall proportion of the contribution of the variance of each of the factors will still remain the same, but not necessarily the correlation will become zero. So this is where we are using oblique rotation, right? So if at all I want to bring in the correlation from my data, I can use this concept quite comfortably. So I'll use a GPA rotation package. Let me install the GPA rotation package. Which contains this information. I'll use the GPA rotation package. So let me load this package. Right. Now here I can use the same factanal, which is doing the factor analysis. Right, I can do the same factanal, which is using the factor analysis, with the only difference being I'll use the brand scale as the input, all else remain the same. Factors I'll set to 3, but the only thing now I'll do is rotation. I'll set it to oblimin, which is the oblique rotation. So I'll put it as oblimin, all smalls. So this additional parameter that I am giving, rotation equal to oblimin. So this is the rotation that would be performed on the data. Small changes will happen. If you see here, the uniqueness, this is what is happening. But look at the factors now. So overall, if you look at the proportions, it's 19.9, 19.3 and 15.9, making it overall 55%. But at the same time, these are still continued. Now you could see some of the variables are gone altogether, right? Only bargain and value have a very big weightage. Here also the leader and serious have a very big weightage. Not too many variables are present now. Here I could see that the latest is having much bigger weightage. It's even crossing 1. So the clear cut difference between the variables loading onto the factors will come out, and at the same time the correlations are not completely zeros here. So depending on our real world relationships, if I want the correlation between the variables not to be completely zeros, I can go with an oblique rotation. But if I want the correlations to be more or less zero, I can go with varimax rotation, which is what the default rotation that typically happens. You don't find too much of difference. Your final decisions will not change that heavily just by changing the rotation mechanism. They'll be slightly different. The loadings will have a slight difference, and even the correlation matrix that you are seeing on the factors say that these factors are not fully independent. They have some level of interdependence. In some cases there is a negative relationship that is existing between the factors, and if this is what we are expecting from the real world, from a theoretical perspective, then I find in this case the oblique rotation would be a much better solution rather than going with a varimax kind of a rotation. So there is nothing that says that oblique rotation is better than a varimax. Data which is correlated, the factors which are correlated, there is nothing which says that this solution would be a much better than an orthogonal one where the factors are not at all correlated. There is nothing that says. It's purely based on my business knowledge. It has nothing to do with the statistical analysis there. Business wise, I need to have some kind of an understanding which says this particular mechanism, these particular variables, these particular factors are correlated in the real world. So I really want even my factors to be more or less correlated. So that kind of stuff will typically be a much better thing to decide whether oblique rotation is required or not. And then I can, okay, it's better that I save this, right? This entire factor analysis, I'll call it as brand FA, brand factor analysis, so that I can take the loadings, right? Item to factor loading if I want to take. I'll take it as brand FA dollar loadings. So each item, so I could see now overall 19.9, 19.3, 15.9. So I'll get how much has been loaded by each one, and if required I can very well take a heat map as well. So I'll take the loadings, I'll take the heat map. So for heat map I need to have the heat map.to function. I think I need to load the package. I don't think it is loaded. So I need to load the package which has that heat map 2. Gplots is the package that contains heat map 2. So let me load that package. So once this package is loaded, let me try doing the heat map 2 again. So this is how it's coming out, right? My factor 1, I can play around with all these things, but my factor 1, right? Otherwise it's better that this is the default thing that it is giving. So red and yellow kind of a combination. So if required, I can very well go with right. I can very well go with the color brewer. It's always better to load your color brewer package, wherein so I'll call it as R color brewer. This is much better package to use, right? Especially if the colors are not coming out that appropriate, I can set my colors more appropriately. So instead of directly doing just doing the basic brand loading, I can set my color, wherein I can use the function called brewer.pal, and I can give my colors. So whatever is the different variants that I want to give, let's say greens. I'll give the greens color, right? You could see what happens here. So different variations of the green is going to come, right? The different variations of the green is going to come. I could clearly see that the dark greens are much better a representation of the overall stuff. So the dark greens, wherever they are, it clearly gives me an indication that these variables are stronger, right? If not 9, let me set 5. So overall 5 different stuff I'm getting here. So I could clearly see this is stronger here, this is stronger here. Serious and leader are very strong in factor 2. The latest is very strong on factor 3. And so probably I can very well go with such a kind of a differentiation, right? So bargain value are looking very strong on factor 1. Leader is looking very strong on factor 2, along with serious and perform, which are looking slightly moderate. And latest is looking much stronger on factor 3. So there is a clear instruction that is coming out in all these different variables. So this is another important or better reflection of the visualization of the item factor relationships. So apart from heat map, I can also go with a path diagram. So which shows a very interesting path for the entire thing. So I can go and install a semplot package for that, and I'll use sempath function from that particular package. So let me install the semplot package. Right. I'll use the semplot package. This is also an interesting way of visualizing my exploratory factor analysis. A path diagram which typically draws before it installs, let me showcase it. It actually draws a visual representation of your entire factor analysis model. So we can look at some of the things here. Once it installs, there's a very interesting representation of the entire factor analysis. It talks about, I can define my cutoff. So anything, any loading that is more than 0.3, only include them. But if the loading is less than 0.3, I can very well omit it. Positives and negatives, I can give them different colors. Positives, I may want to keep it in green. Negatives, I may want to keep them in red. So that way I would like to adjust the colors for the positives and negatives. And at the same time, if I want, I can also manipulate some of the things, adjusting the size, text size, number of characters, etc. So the most important, these 2-3 things. Let's first try to let me load this package called Semplots. Okay, semplot. So let me load this package called semplot. Within this, I'm using a function called sempaths. So the sempaths is giving me the entire path, the path diagram. So let me use this function called sempaths, wherein I am taking my data brand scale. This is the data that I am taking, and I want to get the estimated values. So this is where I say what equal to est. I want to get the estimated values based on the diagram. I don't want the diagram of the residuals which are not contributing to the factors. So those particular unique values that are not contributing, that are not a part of the factors, I don't want any display for them. The cutoff point, I want to set it as zero point 0.3 or 0.5, whatever it is. Now for the positives, I can set a different color by using Pascal. So wherein I can set the values right from, I'll set right from white, right, I want right from white to dark green kind of aspect. So if I have value less than zero point 0.3, less than the cutoff point, it will be set to white, and everything that is above the cutoff point, it would be set to the dark green. Then similarly, I can set the negative color separately, wherein again I can set something like that itself. Anything less than minus zero point 0.3 would be set to white, and others I can even much below minus zero point 0.3 I will set it to red. So some such kind of stuff I can very well set, and probably when I am working out, object is not recognized as SCM model. Why? Oh, sorry, I have to give not this. The factor analysis output is what I have to give as the input, not the data. So what is our factor analysis output here? Our factor analysis output is brand FA. That is our factor analysis output. So I have to give brand FA as the input. Right. So this is taking brand FA as the input. So once I take this, I have the factors, factor 1, factor 2, factor 3. So FC1, FC2, FC3 is what it is showing, and it is giving the values. So the bargain value rebuy, they are going as a part of factor 1, and in this factor 1 I could see that these two are pretty dark, whereas the rebuy is looking pretty much lighter. Similarly, you look at factor 2, I could see the perform, right, leadership looking very strong. Even the SRS is looking much stronger, whereas the fun is looking negative. So that is what we are calling as factor 2, and factor 3 is loaded on latest and trendy. So latest is looking much stronger, the trendy is looking slightly much weaker. So greens are representing the positives and the reds are representing the negatives. So the latent variables are shown at the top. They are drawn with circles. It's a very interesting way of assessing the interactions between the variables quite comfortably. So color shows positive, negative, and the thickness typically depicts the strength of the relationship that is existing between the factors and the various variables as well. Then, now I want to use the factor scores typically to interpret the data, right? Let's say I want in this example itself, different customers have given different kinds of ratings to different brands. So when they have given different ratings on that 9 variables, Now I have some kind of scores that are computed based on those three latent variables or factors. Corresponding to the 9 inputs that the customer has given, the three latent variables are computed and the factors are typically, the scores for the factors are computed. So interpreting the factors is as good as interpreting the 9 variables. So I don't need to really interpret the 9 variables separately. I can in fact interpret the 3 factors which are representatives of the 9 variables. So I am able to concentrate on a smaller and more reliable set of dimensions rather than looking at the overall set of data as such. Now that itself is a very important improvement in the process. So if I really want to get that particular aspect, which is getting the scores for each of the data, I can use one more in my factor analysis variable. In my factor analysis function, I can very well set scores equal to Bartlett, which will actually give the scores also, the factor scores for each of the 1000 records. I'll get the factor scores for each of the 3 factors. I can save them to a separate data, and if required I can analyze on them. So probably I'll call it as brand scores if required. We'll create one variable called brand scores, wherein I'm doing a factor analysis, right? We perform the factor analysis first. Brands, let me call it brand scores. Let me call it as brand SS. So first let me perform a factor analysis. So I'll take the brand scale as the input. Then I'll set factors equal to 3. And I'll have to set rotation, right? I can keep an oblique rotation, or if I don't put a rotation, fair enough, let me keep the default rotation itself. And I can very well set my scores as Bartlett. Scores, I'm setting it as Bartlett this way. So this Bartlett scores will give me a brand SS, which is where the scores are very much captured. So now I can create a variable called brand scores, which I would get from brand SS, which is my model that got created, right? Brand SS dollar scores. And if required, I'll save, this has to be saved as a data frame. So I'll put a data frame on the top of it. So rather than a list, I'll convert it into a data frame. So my brand scores, these are the things that are coming out. And now I can very well do a head of brand scores. So this is the kind of scoring that I'm getting for each of the factors on each of the data. Now if I want, I can do aggregations, everything I want. If I really want to check out the values across the brands, so you could look at the tail of brand scores as well. Now even there are 1000 records with these kind of values. Now you can do an aggregation of these across brands. You want to do some kind of calculations for different brands, you can very well do it. Or you want to do some kind of segmentation based on this, you can do it. You want to do some kind of so now it's like 3 more columns of data, right? You want to compare which brands are there which are good at factor 1, factor 2, factor 3. So probably to this brand scores, right, let's say C bind. Let me do something like this. So brand scores, I'll create one more variable called BS, where I am doing a C bind of the original brand scores, and along with that I am doing, right from the original brand, I am pulling the 10th column, which is the brand names. So I am binding these two things. So I could see now the head of BS, if I am setting I am getting it as a kind of stuff. Now I can do the aggregate, right? Probably let me rename names of brand, sorry, BS, and out of that I look at the fourth one. Let me rename it as brand name. Okay, brand name is, I have to put it in quotes. So now I could see head of BS. Yes, I get my heading as brand name. So now if I want, I can very well aggregate the stuff as well. Right, let me now it's as good as any other data, so I can say BS mean. I'll take a mean of each of the factors. So this is where I'll say aggregate, where I want to aggregate all the values across the brand. So aggregate everything across the brand. So I'll say all the values dot brand name. So I want to aggregate all the values across the brand where the data is BS, and I want to take the mean of all of them. So I get my formula must have both right hand and left hand side. Okay, let me do an aggregate of factor 1, factor 1 dollar brand name. So I'll get BS mean. So when I'm looking at the same thing, I can look at for factor 2, factor 3. Okay, so the other way I could have done this is first put a dot tilde brand name. So it will typically do factor 1, factor 2, factor 3 across the brands. So I'll get a head, I can look at the head, or I can simply look at BS mean, which is the mean of the brand scores. So I'll get each of the values for each of the means, right? Each of the factors, I'll get the mean values for each of the brands. Now based on that, I can very well create a heat map. Brand wise, I can create heat map now. So I'll take heat map dot 2. Let me take the heat map dot 2. I'll take as dot matrix. This requires a matrix only, and I'll give the inputs only from BS mean. I'll omit the first column. I'll take all the rows, omit the first column. That can still be taken as a matrix. I'll compute the heat map on the top of it. So this is what is coming out as a part of my heat map. So the ones that are more and more yellow talks about being very strong. Otherwise I can use the same color brewer kind of stuff again as a part of my brewer pal. I can very well use it. So let me use the, now that we already have the R color brewer already installed. I'll typically set color equal to brewer dot pal. The 9 colors I'm setting, and the kind of color code, if I want to set, if I set it as GNBU, it will be green blue kind of a combination. So let me close this here. So we get a green blue kind of a color, greenish blue. So the ones that are in the dark blue, they are very strong. So in factor 2, I could see that these are very strong. I have to give BS mean for each of the brands. So I could see now the brands 2 and 3 are strong on factor 2. Then I could see that brand 6 and 7 are much stronger on factor 1, and a few brands are not at all present in factor. So we could clearly see which brands are stronger in which of the factors, right? You could see that brands F and G, 6 and 7, they are more or less similar on factor 1. Then B and C, which are 2 and 3, are similar on factor 2, and so on. So this is how we can go more and more deeper in terms of analyzing the factor scores across the brands. We can do aggregations, we can do heat maps, all such kind of an analysis can be done more and more comfortably. So just to conclude, exploratory factor analysis is a very valuable way to examine the underlying structures and the relationship between the variables. It reduces the data complexity by grouping the variables, creating a very small subset of latent variables which will aggregate the multiple variables, which can be simplified into 2 or 3 dimensions rather than looking at a broader set of 9 or 10 variables. Now that's the major advantage that we can derive using the factor analysis. So these are the various things we have looked at as a part of this session, right? If you have any further queries on the same, you can very well get in touch with me by giving me a call on the number that I have provided below, or you can send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.